So our next question is actually an inverse question. It comes from machining. It's actually a question that comes from Buhle machining. And Buhle machining, this question looks like a lot of questions that you guys sent to us. They look almost the same because they're dealing with functions and inverses of quadratics and straight lines. So I'm going to pick one that is going to try and cover all of you guys. So after we do it, you can see what is happening with a quadratic. When you have a quadratic, how do you work its inverse graph, and how do you draw it, how do you analyze it, those kinds of things. That's basically what I'm going to be doing. So let's check this one here. It looks like Buhle's question, which looks like a lot of the other questions that you guys sent to us. So it's inspired by Buhle machine in this question. So let's look at it and help you to understand what is going on. So we are told here that f of x is equal to, we're told that f of x is equal to negative 3x squared, right? And there's nothing else that actually appears on the question. That's all that we are told. Now, the first part here says we need to determine, right? Let me put the questions here. Number one, the examiner wants you to find the equation of the inverse, right? Find the equation, right, of the inverse of f of x in the form, there we go, in the form. You must respect examiners. They get very pissed off if you guys don't follow their instructions. So when they say in the form y equals to whatever, you must respect that. And there's a reason why they would want you to write it in a form y equals to something. And I know, like, we just take things for granted sometimes, but there's a flaw in always calling everything f. You can't keep calling things f of x, because you guys sometimes call relations that are not functions f of x. The whole thing, the whole notation of f of x or g of x or h of x is only reserved for functions. So you can't use it when you are discussing something that is not a function. It's wrong. That is why examiners want you to write it in a form y equals to whatever, because they know that the inverse graph might not be a function. Not all inverses of functions will become functions. Sometimes you need to be able to do some editing or some engineering on a function so that it becomes, so that its inverse becomes a function as well, right? Not all relations are functions. And even when you have functions, not all their inverses will be functions. Be careful of that. For example, this one we're looking at here is a function. A parabola is a function. But if you're going to do its inverse, it's not going to be a function. Its inverse will not be a function. That's why they're saying express the inverse in the form y equals to something, because it is illegal to write the inverse of a parabola using f notation. Be careful of that. Educators, please correct the kids. All right, now let's go to the second part that they wanted us to look at here. The second question that they want us to look at, they want us to draw them. Okay, they say domain and range, yeah. They want the domain and the range of both, right, f and its inverse, right, of both graphs, okay, or of both relations. And then lastly, they want you to draw them. They want you to draw them. They want you to draw these graphs, right? Okay, cool. So let's see what we can do with this. There's more, of course, that you guys wanted us to look at, but I think this covers more of you based on the questions that you guys have. It will generalize and cover most of the questions that you have on working with functions. So the first question says we need to find the equation of the inverse in the form y equals to something. Like I said, the process of finding an inverse is very simple. That's actually what is new. That is the only thing that is new. Just swap x and y. School out, right? So I've got y equals to negative 3x squared. I'm looking for the inverse graph. We agreed that in order to find the inverse, where you see y, put x, and where you see x, put y, and everything else needs to stay the same. From here, I will then need to, of course, make y the subject of the formula. So I'm going to have to divide both sides by negative 3. So I'm going to divide here by negative 3. I'm also dividing here by negative 3. That cancels out. We get y squared equals to negative 1 over 3 x. So we don't want y squared, we are looking for y. You need to find the square root of that. And if you've been watching the show, you remember something that I said about finding square roots. You'll correct me. Please shout it out at home so that they can see that you're benefiting. What mistake did I do here? Yes, I can hear somebody saying, sir, you forgot to put a plus minus. You need to put plus minus every time you introduce a square root. So I'm going to say then, therefore, we can conclude that your y is equal to plus minus the square root of negative 1 over 3 x. That's actually this story here. Now, it is important, it was not in the original question. There was no restriction in the original equation. But if you look at this graph that we have here, you will agree with me that there are x values that we can't use if we ever had to draw this graph of y that you're currently looking at. If I put any number in this question that happens to be a positive value of x, which means if you think about the Cartesian plane, because I want you to understand what I'm going to write now. I'm going to write like a restriction for my x values. Not all x values can be used here. I need you to pay attention to that. Remember, the Cartesian plane, right, has got positive and negative x values, right? Now think about anything positive. If I take a positive number, right, even if I take a 1, and I try to sub it here, if I sub a 1 there, right, I'm going to have negative 1 over 3 times 1 under the square root sign. And you guys should see that we've got a problem now, because you're going to have plus minus the square root of negative 1 over 3. And we know that the square roots of negative values produce things that are non-real. And in the context of our high school's work, we don't want to work with graphs that have got non-real values, which means we're not discussing complex numbers. We're only interested in real values. So that means that all the positive values of x are not supposed to be considered when we're working with this graph. So I would like to be nice to the examiner and tell him that in this graph, please focus on the x values that are only less than or equal to 0. Please focus on the negative values, because if you take anything negative here, like negative 1, when my 1 changes to be a negative, I'm going to have negative times negative, which is going to give me a positive square root of 1 over 3, which we are happy about because we know the solution to that. So be careful. The graph is only defined on the left-hand side of the y-axis, only for the negative x values. That's actually very important. So I want us to only focus on all those x values that are on the left-hand side of the y-axis. Very important for us to keep that in mind. Right, so I'm going to remove this. I hope this actually helps you guys to understand what is going on. We can't accept positive x values. They'll give us square roots of negative values, which are non-real, and we are only interested in real values. Very important. So that is the solution to the first part of the question. Now I'm going to the second part that says we need to write down the domain and the range of both the graphs. Ooh. Okay, so I'm going to draw a rough sketch of these graphs. This is the mother graph of an example of a simple parabola. So the original graph of f of x has the equation negative 3, right, x squared. And its inverse has the equation y equals to plus minus, right, the square root of negative 1 over 3x. This is what we are sitting with. Now this is the mother graph of a parabola that is facing down, the set face parabola, the one which is concave down. You guys should know this, because we know that this number here tells you whether your graph is going to be a happy face graph or a set face graph. So we know for a fact that this one is facing down. So I'm going to draw it in yellow, and I'm going to put it like that. So this is the graph that we're dealing with. If you had to draw it accurately on a Cartesian plane, if the examiner happens to give you a graph paper, you will then use a table for these ones. These are the ones that you use a table for them, right? It is obviously turning at 0 and 0 there, right? And of course I can be nice and tell the examiner that if you have an x value of 1, the corresponding y value is going to be negative 3. That's very important. If you sub 1 on that, you're going to get a value of negative 3. Just being nice to them, telling them that it passes through that point as well. Now, how would the inverse look? How would the inverse look? Like I said, the inverse will simply be what you get when you try to reverse what you have on the original, right? Let me be nice again. Let me put another point on the original graph. Let's call this one the yellow graph. The yellow graph is the original graph. When x is 1, its corresponding y value is going to be negative 3. And when x is minus 1, its corresponding y value will still be minus 3. Very important, powerful. Okay, so now I want to find properties for the inverse graph. If I've got information, right? If I've got information from a table of or whatever, right? From a table or whatever. In fact, I think I should use a table so that you guys will appreciate the power of the story of inverting stuff. The table for the original graph would look like this. This is what the table for the original graph could look like, right? I'm only taking 3 values. X, right? And I want the corresponding y values. I want minus 1, I want 0 and 1, right? So if you take that minus 1, you substitute in the graph of f, it is going to give you a corresponding y value of -3. If you take 0, you substitute in the graph of f, it will give you a value of 0. If you take 1, you substitute for x, it's going to give you a y value of -3 again. So this is actually how the table of the graph of f is going to look. Now, if I want to draw the inverse, I don't actually redo everything that we've just done. What I simply do is I just say I'm going to swap them. How do you swap them? Well, everything that is x becomes y, and everything that is y is going to become x. So this is x and this is y. So you take all the x coordinates, you put them as y values. So that -1, 0, and 1, I'm going to write them here, -1, 0, and 1. So all my x coordinates are now called y coordinates, and all my y coordinates are now going to become my x coordinates. So which means my -3, 0, and -3 are going to be my x values, right? And then let's call the Cartesian plane and draw this one in blue. Blue will do, right? Let's use blue for this one, right? So this is what we are looking at. It's going to pass at 0 and 0. It's going to look like this, right? This is what the inverse graph of this is going to look. That's the graph of the inverse. Where is it passing? Well, you'll agree with me that when x is -1, when x is actually not -1 but -3, yeah, when x is -3, the corresponding y value is -1. And when x is -3 again, the other y value is 1, and it's also passing through 0 and 0. This is how you would draw the inverse graph using the information from the original if anybody was asking you to draw them. So let's go back and see what the question was saying. It was saying to us that we need to write down the domain and the range of both those graphs. And I just answered number 3 because I think number 3 is good to help you understand what is going on with question 2. I just drew them, right? Okay, cool. So the domain is asking for the x values, and the range is asking for the y values, right? The domain are the input values, and the range are the output values. So the domain, let's look at the domain. The domain are the x values. So this graph that I'm looking at, the yellow graph, right? The graph of f of x, the original one. What are the x values that this graph is covering? You'll agree with me that the graph is not limited in terms of moving left and right, right? So think about it. In terms of moving left, the graph is not limited. In terms of moving left and right, there are no limitations. There's nowhere where the graph does not reach. So it covers all x values from left to right. So I can simply say the domain of this graph is all x values. It covers literally all x values because moving from left to right, the graph is not limited. So my domain is going to be x is the element of real numbers, right? So let's jot that down. The domain is x is the element of real numbers. Now, the range of the yellow graph, the range. What are the y values that the graph covers? Now, if you look at the yellow graph, you will agree with me that there's no yellow graph above the 0 point. From this point here, from the turning point of the graph, right? From the turning point of the graph, if you start here and you move up, we don't have a graph. There's no graph there on top. The graph starts from 0 and is covering all y values moving down. So this graph exists when you're going down. When you're going down, the graph does exist, but when you're going up, then there's no graph, which means this graph is covering all y values from 0 going to -infinity. It is there where the graph is defined. It's defined for all y values that are less than 0. So that's what I'm going to write down as my range. So I'm going to say to the examiner, the range of the graph is y is all values that are less than or equal to 0. Some people don't like that notation. You can use this format, set notation, by saying y is the element of, and then you put a square bracket. No, let's start with a small number because we're going to -infinity. So I'm going to say, examiner, this graph starts from -infinity and goes all the way up to 0. We start with the smallest number from left to right. So it does cover -infinity, but it stops at 0, and it does include. Notice my brackets there. I'm using a square bracket at 0 because it does arrive at 0. And I'm using a different bracket for infinity because nobody can reach infinity. Very important. Okay, now in order to write properties of the original graph, I have them. Now I'm looking for the domain and the range of the inverse, right? The domain and the range of the inverse. So like I'm sure you can now figure out what is going to happen. Like I said, you just swap. What is domain will become range, and what is range will become domain. So let's start with the range. I'm going to take what was written here and write it there. right? So the domain of this graph will be the range, which means the following. The range of the graph is going to be y is the element of all real numbers. So I'm going to say y is the element of real numbers. And this is suggesting that this graph has no limitations on the y-axis. It covers all y values. Let's go and check if this is making sense. Does this graph cover all y values? Yes, you'll agree with me that in terms of moving up and down, this graph has no limits. It moves as far up as it wants, and it moves as far down as it wants. So it covers literally all y values. That's why its range is going to be y is the element of real numbers. Now the domain, I'm going to copy the range of the previous graph and call it the domain of its inverse, which means, beautiful people, the domain of this one, instead of saying y, is going to say x is less than or equal to 0, and the alternative notation will also be x is the element of negative infinity all the way up to 0, including 0. So I'm sure you can see how this is actually working. And think about it. Let's go back and look at this graph. Does this graph cover positive x values? I don't think so. Look at it carefully. And I'm going to use a yellow marker to show you that this graph is only defined from the y-axis moving to the left. We do have a graph there. We have a graph from the y-axis moving to the left. But we don't have the graph on the right-hand side of the y-axis. That's why this graph only covers negative x values. And then we then say to you that the domain will be all x values that are smaller or equal to 0, and that will be how you would need to work with this. Now you might of course be interested in drawing these on the same set of axes, but according to this question that was sent to us, we didn't really need to do that. And some people might also even ask you to find the point of intersection of those two graphs. Then you will have to equate them and solve for x and y. Let's just go and see how that would be, how will that be done, right? How will that be done? So this one says, okay, maybe let's find the point of intersection. The point of intersection of the f of x and its inverse. Okay. Now, if I had to draw them on the same set of axes, right? If I had to draw them, I'm going to do a rough sketch now. They were going to look like this. Remember, the yellow graph is a set face parabola, and it's passing at 0. The inverse is a parabola that is facing to the left-hand side, so they look somewhat like that, right? Now, the important thing you need to pay in mind, that you have to pay attention to, is the fact that the line of symmetry for these, like we told you before, the line of symmetry or the mirror image is by the line y equals to x, which is going to be a line that passes through where they intersect and also passes through where they intersect there at 0, 0. So that will be the line y is equal to x all the time if you had to draw them on the same set of axes, right? Very important for you to keep that in mind. So if we wanted to find the coordinates of the point of intersection, we're interested in these coordinates, which we already know they should be 0 and 0, and whatever this is going to be, right? And you can be ambitious and try to solve for x there by equating the equations of those equations. Remember, the first one was f of x is negative 3x squared, and the second one was y is plus minus the square root of negative 1 over 3x. Now, in order to find the point of intersection of any two graphs in the world, it doesn't matter where you are. If you want to find the coordinates of the point of intersection of those two graphs, it means it is where the graphs are equal. So I'm going to equate them. I'm going to have negative 3x squared is equal to plus minus the square root of negative 1 over 3x. And then we just apply our algebraic skills and have fun with this. Let's have fun, right? So what do I hate here? I hate the square root. I'm going to square on both sides. What you do on one side, you need to remember to repeat on the other side. This is the law of conservation in mathematics. It says what you do on the left, you need to repeat on the right hand side. So the square of anything is always positive, and the square will remove that square root. So that plus minus disappears because the square of anything is always positive. I'm left with minus 1 over 3x. Now this here is going to be negative 3 squared, which is going to be 9, and x squared squared is going to be x to the power of 4. And then you just do what we call, you can multiply both sides by 3, because I don't like that fraction there. If I just multiply everyone by 3 to undo division by 3, it's going to be 27 x to the power of 4 equals to minus x, right? And then you then take this one to the left. I'm going to have 27 x to the power of 4 plus x equals 0. And then you just solve for x by taking out a common factor, which is x. You've got 27x cubed plus 1 equals to 0, and then from here you then say x is 0 or 27 x cubed plus 1 equals to 0, which you can then simplify by transposing. You'll get x cubed equals to minus 1 over 27. When I take 1 to the right and divide both sides by 27, and you remove that 3 by taking the cube root. You take the cube root of this. You also take the cube root, beautiful people, of negative 1 over 27. And if your math helps you, or your calculator helps you, you're going to get a solution of negative 1 over 3. So it's very important for you to understand that the cube root is not plus minus. In fact, all even exponents will have plus minus, but odd ones will not have. So if you're taking the cube root, the 5th root, the 7th root, the 9th root, you don't need to put plus minus. But for the square root, the 4th root, if you're taking the 6th root, any even exponent, if you're taking the root of an even power, you always need to put plus minus. But the odd ones, don't worry about them. Right. So then we've got minus 1 over 3 and 0. If I'm looking for the corresponding y values, I can pick any of those graphs, right? I can pick any one of them. I can just substitute 0 either in the graph of negative 3x squared. I like that one. Where is it? Oh, there it is. I'm going to use this f of x is negative 3x squared to figure out the corresponding y values. So I'm going to substitute and say, okay, f of x is negative 3x squared. So I'm looking for f of 0, which is going to be negative 3 into 0 squared, which also gives us a 0. That proves that they intersect when x is 0 and y is 0. And for this one, I'm also looking for f of negative 1 over 3, right? That also says the graphs are intersecting when x is minus 1 over 3, which we can then simplify to negative 3 into negative 1 over 3 squared. And if my math is still up to scratch, this is negative 3 times 1 over 9, which is positive because anything squared is positive. So this becomes positive 1 over 3. Therefore, the other point of intersection is minus 1 over 3 is to minus 1 over 3. Right, very powerful. So these are the point of intersection of these two graphs, which I can go and put there in the drawing that we guys just discussed now. This point here will be negative 1 over 3 into negative 1 over 3. By the way, I didn't really need to find the corresponding y value because these graphs are symmetric by the line y equals to x. So the y value is always equal to the x value. These are always equal if you are looking for the point of intersection. So if you know one of the coordinates, you don't need to work out the other one because all these three graphs intersect at the same point. They intersect when y is equal to x. So this is actually what you could have done in order to find the solution to these questions. A very, very nice question. I hope it has helped you to understand what are inverses. How do you work out with an inverse quadratic function? It hasn't really said anything about an inverse being a function or not. We're drawing the graph, drawing its inverse, finding the equation of its inverse, and finding the point of intersection of these two graphs. By the way, a parabola is a function, but the inverse of a parabola is not a function. Let's hope somebody's asking, what do you do to the inverse of a parabola to force it to be a function? So if you want to see more engineering that we do in math in order to force things to suit us,